Okay, I hope you can hear me. I sort of blame Trevor for this because I think I loaned my microphone to him and I can't get it back right now. Okay, so here's our, let's just try this first one. So this is kind of funky, but we've got here this plate. Let's see, the plate, it's 5 by 5 5 meters by 5 meters, 400 degrees C. It's suspended vertically in a very large room that has a temperature of 25 degrees C. And the plate gives you the emissivity of the plate and then asks for the net heat radiated from the plate. So some clues here. This net heat radiated means this idea that the plate is suspended inside of a large room. So the room itself is transmitting heat to the plate, and the plate in turn is transmitting heat. So the Q net is going to be equal to, the Q dot net is going to be equal to the Q dot net from the plate from one, excuse me, not Q dot net. It's going to be equal to the oh, I'm supposed to be erasing this. It's not working very well. It's going to be equal to the Q dot of 1, which is the plate, minus Q dot of 2, which is the room. We'll call the plate 1, we'll call the room 2. So it's the difference between those two, the difference of radiant heat. Now, notice that it's suspended vertically, so that's another clue to us that if you've got this plate suspended like this, you're going to get Q from this side, but also from the back side. So we have to keep track of both sides. We have the temperature, we have the temperature of the room. We're looking only at the radiated heat, and it's the rate. Probably they're looking for something in terms of kilowatts. So they're looking really for the power that is being, the power of heat that is, or the heat per time. Okay, so let's clear the screen and let's go ahead and work on this problem. I don't know how to do that. So we'll go ahead and make another drawing. We've got this plate. We know that it's 5 meters by 5 meters, and it's suspended. The room is 25 degrees C. The plate itself is 400 degrees C. And we know that the equation that we have from the Fe materials, Q dot is equal to A times sigma times epsilon times t to the fourth. This isn't enough information. We actually have to use the other equation that accounts for the object receiving radiation from the room, from the very large room. Okay, so that's another clue. This notion of this very large room is telling you that in this equation, which looks like this, A1, so the 1 would be the plate, times sigma, which is the Stefan-Boltzmann constant, times F1 to 2, T1 to the fourth minus T2 to the fourth. So what we have to evaluate here is F1 to 2. And in this case, because the room is very large, this value right here is essentially going to collapse onto epsilon 1 of the plate. Now you can see that some assumptions that we're going to make are that the edge here contributes negligibly to the radiative effect. So we'll just use the area of this plate, which is the A1 is going to be equal to 5 meters times 5 meters times the two sides. So that is equal to 50 meters squared for A1. I believe epsilon 1, and now I don't recall what it was in the problem, is 0.12, is 0.12. Okay, so let's just go ahead and figure this out. We've got that Q1 is equal to 50 meters squared times the Stefan-Boltzmann constant, 5.67 times 10 to the negative 8th watts per meter squared Kelvin to the fourth times 0.12 times t to the fourth for T1, T2 to the fourth. Now these are both in absolute temp. So this is in Kelvin. So wow, that didn't come out very well. Okay, so we need to convert the T values to Kelvin. So the temperature 400 goes to 400 plus 273 is 673 to the fourth minus 298 to the fourth. And I'm going to use a calculator for this part. I'm going to pause. What I got when I did this is I got 67.1 times 10 to the third. And let's just check the units. I believe that will be kilowatts, but let's just make sure. So we've got meters squared times meters squared divided by meter squared. Those drop out. This is going to be Kelvin to the fourth. That will drop out with this value. So that should give us watts. So our answer is 67.1 kilowatts. And that would be the net heat being lost. Really, it's the rate of heat loss. Can't even read that. All right. I hope this is helpful. Bye.